All right, so we're going to quickly go through 4.2 and talk about arrangements of electrons. We're basically going to be dealing with our quantum numbers. So, a couple of things. First off, wave nature of matter. Basically, what we've discovered is we know that light is both a particle and a wave. So we've discovered this at this point. We know it's a particle and a wave. We know that E equals mc squared at the nuclear level. And so what de Broglie basically said was if light can have a dual nature, guess what? Matter can also have a dual nature. So matter can also behave as a particle and a wave. We see the wave nature of electrons when we look at, when we start going through quantum numbers. And we see the wave nature of matter when we look at the Bose-Einstein condensate. Okay? You start seeing matter behave like a wave instead of like a particle. Now, the uncertainty principle, this ties into the probability density maps. So in essence, as we talked about earlier, Heisenberg basically said that we can know the general location. I can know the general location of something, but I can't pinpoint it exactly. In other words, this is why that idea of orbitals is so, most people are very anathema against it in terms of chemistry, because again, we can't pinpoint it exactly. It's not like we can say where the moon is around the earth or where the earth is in terms of the sun. Okay, so this is in essence the point. If I know the general location, I don't know the trajectory. If I determine the trajectory, I don't know the exact location. That's all this is saying. But this does lead us to this idea of a probability density map, and this probability density map is also based on what we call the wave nature of light, or the wave equation. This is what Schrodinger gave us. Now, in the reading that you're doing, it shows you Schrodinger's equation. You don't have to know Schrodinger's equation. All you have to know is that the solution to the equation is what we term quantum numbers, and this is what we term quantum mechanics. Okay? So the corny joke, pause it and read it. Okay, so quantum numbers. When we solve a wave equation, we get a set of wave functions. Okay, in other words, the solution, the set of numbers, the set of quantum numbers, that's what solves the wave equation. Now technically there's a fourth we'll talk about at the end. The first two, principal quantum number. Okay, principal quantum number is always whole numbers, 1 through 7 right now. So it's whole numbers, always. And basically what it tells us is the higher the number, the further away from the nucleus the electrons are found. Now angular momentum is found, it's our L. L is always less than or equal to n minus 1. Okay, so that means if I have an n equal to 1, my L equals 0. If I have an n equal to 2, I have L equal to 1, and I have L equal to 0, because it's less than and equal to n minus 1. So that means it encompasses everything that is less than or equal to what n minus 1 is. So notice that if L is 0, I have what's known as an s orbital. If L is a value of 1, I have a p orbital, and so on. So what this generally gives you, when we talk about angular momentum, it's giving us the general, it's giving us the general shape. Okay, so this simply gives us the general shape of the orbital. Okay, spherical, dumbbell shaped, or cloverleaf. Don't laugh at my cloverleaf. Okay, now that takes us to m's of L. Okay, m's of L is equal to negative L to positive L. So if L was 0, well, guess what? M's of L is 0. But if my L equaled 1, okay, then I have negative 1, I have 0, and I have positive 1. So magnetic gives us 3D. Okay? 3 dimensions. It's the orientation in space. So it's great to know the general shape, but then this tells us the shape in space. So notice that an orbital with the same value is in. So if I have an L equals to 1, okay, that was P, correct? Well, there's 3 different numbers, so that means there's 3 P orbitals. And so there's 3 separate P orbitals. So 1, 2, 3. In other words, there's 3 different ways I can orient that orbital in space, 3D. An s orbital, which is spherical, There's only one way to orient that, so that's why IMS of L is 0. Kind of makes sense. Now, pay attention to this chart. This chart is huge. You want to pick up on the patterns. There's a couple of patterns you can pick up on the value of N and the number that's going on here. You can see the pattern in terms of the values and the number of orbitals at each level, etc., etc. The other thing you want to be looking at is, remember that the periodic table isn't random. So this is actually giving us a little look into a little of the inherent nature of the periodic table and how it's organized. Okay, so s orbitals are spherical, p orbitals are dumbbell shaped, and again, go back, notice that as I increase in number, remember increasing number meant I was further away from the nucleus. Well, sure enough, notice how the orbital is bigger each time. P orbitals, again, we said there should be 3 of them, right? -1, whoops, let's erase that, undo. -1, 0, +1. Well, sure enough, there's 3 different versions, okay? Because L equals 1 means I'm P-shaped to begin with. And then D, again, notice with D, well, D equals 2. If L is equal to 2, then that means I have to have, well, -2, -1, 0, +1, +2. And sure enough, I see 5 different orbitals, and I had 5 different numbers. So again, that 3-dimensional space, that 3-dimensional shape is showing you there's 5 different ways it could orient in space. Now, this brings us to the last one, which is known as IMS of S, spin. In essence, what happened is when they looked at the electrons, they saw that they tended to go opposite directions. They were parallel. It wasn't like one wasn't negative. They just went different places. Well, what they discovered this means is that we have what's known as spin. This is our 4th quantum number. Okay, an upspin is, we're just going to call it +1/2. Our downspin, we're going to call -1/2. So literally, we have an up arrow and a down arrow. And this orientation is the only way 2 electrons can occupy the same space. Well, guess what? This is the same space. This is the same space. And when I look at one of these, this is the same space. So the only way I can have 2 electrons in the same space is if they have opposite orientations. They have opposite spins. And so it's the same thing. If I have, think of it as a thumb. If I have my right thumb, okay, and then I have my thumb there, okay, if I could literally take my same right thumb and bring it down, okay, that's literally kind of what's going on with my spin. Okay, so I have, if I take my right thumb and put it up and I literally take the mirror image and put it down, that's literally what's going on here. Now, what this means is, let's back up. So I know N is going to be whole numbers equal to 1, or, equal to whole numbers. I know L is going to be less than and equal to N minus 1, meaning it encompasses everything. IMS of L is -L to +L. And my IMS of S is always going to be +1/2 or -1/2. Okay? And the combination of these means I can predict what quantum numbers are possible and what are not. Now, what you want to do, as I said, you need to be linking this to the periodic table. Well, guess what the N equals? That's my principal quantum number. It's going to correspond to the rows on the periodic table. So if I'm in row 1, if I'm on row 1, well, that was hydrogen and helium, right? That's only 2 elements on the whole row. Well, 1s. How many electrons did your table show you a 1s orbital would hold, or an s orbital in general? S orbitals only hold 2 electrons. Well, if I can only hold 2 electrons in the same space, and I know I have the circle, and I put 1 up and I put 1 down, guess what? I can only have 2 elements. So you start seeing and you start making the connection between these quantum numbers, and the structure of the periodic table. So, again, looking back at this. So 1s, so I have s. Well, that means my next row should be 2s, but there's a total of 8. Well, that means there's also 2p, remember? And s is 1 orbital, holds 1 electron. 2p, there's 3 of them, right? So that would be 1, 2, 3, 4, 5, 6, 7, 8. And sure enough, at the end of row 2, at the end of row 1, we had atomic number of 2. Well, at the end of row 2, we have an atomic number of 10. Well, isn't 2 plus 8 10? So you start seeing that connection between what we're talking about here and the order of the periodic table. Now, that ties us into this one when we're looking at how to solve this and recognize valid quantum numbers, N, L, and Ms of L for the 7th electron of chlorine. All right, so when we, and this is what we're going to talk about a little bit more detail in the next one. In essence, when we look at the 7th electron of chlorine, I'm going to tell you right now, when we look at this, the N value, okay, chlorine is in what row? Well, chlorine's on the 1, 2, 3rd row. No, 2nd row. Fluorine, chlorine. Yeah, it's on the 2nd row. So we know it's going to have an N equal to 2. Okay. And here's the other thing. If we're talking the electron, we're literally, remember that the number of electrons equals the number of protons. Chlorine itself is element 13. Let's see, wait. No, we're on the 3rd row, aren't we? Okay, don't laugh at me. N equal 3 because we're on the 3rd row. I know chlorine is element 17, right? 10, that's 9, 10, yeah, and 7. So I know element 17, but I want the 7th electron. So that means I'm literally going to look at what would be the 7th element. Well, the 7th element is on the 2nd row. Okay, it's on the 2nd row. So if it's on the 2nd row, I know I need an N equal to 2. So I'm going to eliminate this one, I'm going to eliminate this one, and this one. Okay, now if I go on the 2nd row and I go to where the 7th one is, well, remember we said S can only hold 2 electrons. So the 1st row, I have S1, S2. Now I have to go to the 2nd row. I have an S1 and an S2, don't I? Well, that's only 4. So that means I have to jump over here. Well, that means at 1s it held 2, at 2s it held 2, and I have to go to 2p. Well, if I go over here to 2p, remember there was 3 orbitals, 2 electrons per? Well, when you look over here, so here was the first 2 columns of the periodic table, and then way over here I have the rest of my elements, don't I? So it goes 1, 2, 3, 4, 5, 6, and so on across, right? If I go to the 7th element, well, 1, 2, I have, that's 4, right? 5, 6, 7. So that means my 7th one should be in a P. Well, what was the value of P? The value of P was 1. So that means I need to get rid of that one. I need to get rid of that one. So I'm down to these 2, aren't I? Well, remember this is Ms of L. Ms of L is negative L to positive L. Well, if my L here for a p orbital is a 1, is that possible? Well, no. So we eliminate it, so we know that's the correct answer. And that's all we're doing. Okay?